welcome back to my system design series. Today we are going to start chapter number 6, that is a partition. We all have heard the word partition, but let's understand what partition means in system design. Imagine you are running a popular e-commerce website called Amazon. As the user base will grow, similarly the data will also grow. And managing this data efficiently is very important. So for that we use distributed databases. System that stores the data across multiple machines to ensure scalability, reliability, and performance. In distributed setup, data is not confined to a single machine. Instead, it is spread across multiple nodes, each handling the portion of the workload. This distribution brings us to our main topic, that is a partition and replication. Let's start with partitioning. Think of partitioning as slicing a large pizza into a smaller, manageable pieces. Each slice represents partition, a subset of your data. In databases, partitioning means dividing large set of data into smaller pieces and storing them separately. This approach enhances performance and scalability. Consider a social media platform with millions of users. Instead of storing all the users' data at one place, the system partitions the user data on the basis of the user's geographic location. Say users of Asia in one location and users of Europe in another location, and so on. And there are several types of partitions based on the different scenario. So first is horizontal partitioning. It divides the data rows into separate tables. For example, the user ID 1 to 1000 are stored into the one partition, and similarly 1001 to suppose 2000 are stored into the another partition. Second is vertical partitioning. It splits the data column. For example, separating users' login credentials from personal information. Third is range partitioning. It uses the hash function on a key, for example user ID, to determine the partition. It divides the data based on the ranges. For example, orders from January stored into the one partition and order from February stored into another partition. Okay. Fourth is hash partitioning. It uses the hash function on a key, for example user ID, to determine the partition. Another one is list partitioning. It assigns the data based on the predefined list, such as regions or departments. Choosing the right partitioning strategy depends on your data access pattern and scalability needs. Partitioning often operates within shared nothing architecture. In this setup, each node is independent with its own memory and storage. This architecture ensures that failure of one node doesn't impact the another node, which enhances scalability and fault tolerance. Companies like Google, Amazon uses this shared nothing architecture to manage their data centers efficiently. Okay, next is replication. We have already discussed much more about replication in our last videos. If you haven't watched that video, then find the link from the description. But in short, replication means duplicating the data across several nodes. Also, combining partitioning and replication gives us the best of both the worlds, that is a scalability and reliability. For example, a partition containing the user data can be replicated across several nodes in the same region. This setup ensures the quick access and data redundancy. As your system grows, you might to add or remove some of the nodes. Rebalancing ensures that the data is evenly distributed. Automated tools can help to redistribute the data, maintaining optimal performance. While partitioning and replication can offer so many benefits, it comes with a lot of challenges. For example, consistency. That is to ensure that all the replicas can have the same data. Second is latency. Data synchronization can include delays. Another one is complexity. Managing partitions and replicas can add some system complexity. But to avoid this, we have to use some best practices such as monitor system performance regularly. Second is implement robust synchronization protocols. And third, as discussed, plan partitioning strategies on basis of accessing data. Okay, let's understand data partitioning basics. In a large library, we wouldn't accommodate the books into a single shelf. Similarly, data partitioning means splitting the huge set of records into the smaller shelves to improve the efficiency and scalability. For example, we divide the books on the basis of genre and alphabet. This way, queries will only search into the one partition instead of the whole library. Partitioning offers clear benefits. For example, speed up lookups and reduces the load and lets us add more shelves when the data grows. Okay, so why partitioning the data? So some of the key benefits are, first is performance. By searching the books only in one shelf, lookup is faster than scanning all the books. Second is scalability. We can add more shelves or flows as the library grows. Third is load balancing. Work is spread across shelves, so no single shelf will become a bottleneck. Another one is manageability. Smaller shelves are easier to restore or reorganize compared to the giant ones. Okay, let's move forward. Another topic is skew partitioning and hotspots. Okay, let's understand by taking an example. Here you can see there are two bookshelves, and in the first bookshelf you can see that the number of books are equal. That means the data is equally distributed. But in another bookshelf, in one partition, the number of books are more compared to the another partition. So, skew happens when one partition gets the more data or more traffic. In library terms, most of the book starts with the letter S. So, that shelf will be overloaded, while others will be nearly empty. A highly loaded shelf becomes the hotspot that is handling more number of requests. If partitioning is unfair, it is called as skew, and an overloaded partition is called hotspot. In practice, a hotspot causes the shelf queries to be slowed down while other shelves sit idle. Okay, so skew means the shelf is holding the large number of books compared to the other shelves. And a hotspot, that is a shelf with a high load, becomes a bottleneck. If partitioning becomes skew, overall performance suffers. The busiest node limits the throughput. We must avoid such imbalances in any key value store. But what if we place the books randomly in each of the shelves? It can spread the load evenly by chance, but with the major downside. You will lose the ability to find the specific book directly. With random placement of a book, you have to search that particular book in each shelf, which is very difficult and time consuming. So it's better to avoid this kind of hotspots because you don't know which node or shelf have that particular book. So randomly distributing the data can reduces the load, but it will increase the search time to find out the particular data. A better strategy is to use book's key, for example, title, author, to choose a shelf. For example, we could decide that author starting from the letter suppose A to M goes into the shelf 1, and the author starting with the letters from N to Z goes to the shelf 2. Or compute a hash of the title to pick a shelf number. Many databases uses exactly this idea, that is a hash partitioning. By hashing the each key, the system spreads the books evenly across the shelf. Partitioning by hash of the key is especially useful to avoid the hotspots and skew. So using hashing provides lots of benefits. For example, balanced distribution. Hashing a key assigns the books into the shelf which contains the same number of books. Even if the title starts with the supposed letter S, their hash values scatter them into the different shelves. Okay. Second is efficient lookup. All data for a given key goes to a one shelf. In effect, library's catalog tells us exactly which shelf holds any book. Each partition of the dataset contains all the information of the particular key, enabling very fast key lookups. So, if every author by letter S is in the shelf 3, you will straightly go to shelf 3. Next is hotspot avoidance. Because keys are evenly distributed, no shelf suddenly hogs all the requests. Even similar key produces different hashes, preventing one shelf from getting overloaded by a cluster of related books. Okay, so next is control scalability. As the library grows, we can add the shelves and rehash the keys. So each shelf stays balanced. This makes scaling out seamless. But here the point to be noted is if one single key or a book becomes very popular, that shelf could still become a temporary hotspot. But this is usually rare in the diverse data. Okay, next is key range partitioning. Imagine splitting your data like in volumes of encyclopedia on a bookshelf. Each value holds all the records whose keys falls in a continuous range. For example, volume 1 store the entries whose starting of the title starts from A or B. Similarly, volume 2 is for C and E, etc. This is similarly like a library. If you know the book's first letter, you go directly to the correct volume. In a database, if you know a key's range, you immediately know which server or a shard will have that data. But what if data is uneven? Partition boundaries must adjust. You might start with a guess like one volume per two letters, then measure the size of each partition. If one partition is much larger, you can break it or move its boundary. These boundaries can be chosen in the two ways. First is manual selection. An administrator sets the cut points based on the domain knowledge. For example, split between letter J and K because most of the words are before letter J. Second is the database samples keys and picks the boundaries to balance the load, resplitting the partitions behind the scenes if needed. Either way, the goal is to keep the partitions balanced. Adaptive boundaries means one partition might cover a short key range and another a little longer one, so that each ends up with a similar amount of data. Within each partitions, the keys remain sorted. This is a big advantage because it makes the range queries much more efficient. For example, if you want all the keys between 1000 and 2000, you can scan the partitions data within one shot. Sorted partitions allows queries like give me all the orders between January 1 to January 31 because the database only reads that slice in an order. Okay, let's understand the hotspot problem in the range partition. For example, if a raw timestamp is used as a key, it will create a hotspot. All the sensors write the new data with today's timestamp. So, all the incoming writes will go to the current partition. That partition server will get overloaded with the writes while older day partitions sit idle. In database terms, this partition becomes a hotspot which will eventually slow down the system. So, here is the simple fix. You can use the sensor ID along with the timestamp. For example, use the sensor, suppose A, B, C, whatever it is, then colon and then timestamp. Now, partition is effectively first by sensor and then by timestamp. With many sensors active, writes are spread across multiple partitions. Now, if you want to query a time range for multiple sensors, you issue the separate range query for every sensors. But each query remains efficient in its own partition. So, prefixing the keys in this way prevents any single partition to become a bottleneck. Okay, the last thing is different databases call the different words for these partitions. So, MongoDB and Elasticsearch call partition as shards, HBase calls it region, Bigtable calls it tablet, Cassandra and React calls it vnode, and Couchbase calls it vbucket. So remember this word so that whenever someone is referring partition as a shard or region, you will able to understand and relate. Okay, that's it for today's video. We will cover the remaining stuff of partition in the next upcoming videos. So if you are still watching this video, then kindly please make sure you like this video, comment your reviews, and don't forget to subscribe my channel. Thank you so much for watching.